So let's start with Stark effect and Zeeman effect. I think Stark effect is when atom is placed in an electric field, and Zeeman effect is when atom is placed on a magnetic field, and the splitting of energy level inside that atom, that is the two effect that they observe.
You've got the core idea. The Stark effect is indeed what happens when an atom or molecule is placed in an external electric field. The energy levels shift and sometimes split. The Zeeman effect is similar, but caused by a magnetic field. In both cases, energy levels split, and we observe multiple spectral lines where there was previously one. They are key in understanding interactions between atoms and external fields.
So, when do they observe this thing, and why they need to observe so that they can get useful information, or they theoretically formulate when you place something atom particle in an electric field, how that electric field is going to affect its energy levels inside that atom.
They observe these effects experimentally using spectroscopy, basically shining light on atoms and measuring how the absorbed or emitted light changes. In the Stark effect, by applying a known electric field and observing how spectral lines shift, they can deduce the internal structure of the atom, like the distribution of electrons. Similarly, the Zeeman effect reveals magnetic properties and fine details of energy levels. These effects help confirm quantum mechanical models, refine atomic structure theories, and even measure fundamental constants. In short, it's a bridge between theory and experimental validation.
So, like distribution of electron, what you are talking about, this thing, meaning that if that is exposed, how that electron is being distributed.
When I say distribution of electrons, I mean how electrons are arranged around the nucleus, essentially which energy levels or orbitals they occupy. Both the Stark and Zeeman effects reveal subtle shifts in energy levels, and since those levels depend on electron configurations, we can infer how electrons are arranged. In other words, these shifts tell us about the structure of the atom, where electrons are likely to be.
And what is the application? But I think energy level shift and this distribution of electron, how that is related.
The energy levels in an atom depend directly on where electrons are and how they interact with the nucleus and each other. When you apply an electric or magnetic field, the energy levels shift or split. These shifts reflect how tightly or loosely electrons are bound. By measuring these shifts, we understand how electrons are distributed in orbitals, which is crucial in determining an atom's structure. This knowledge has practical applications, from understanding materials' properties to developing technologies like lasers and quantum devices.
Okay, for lasers, can you give specific examples so that I can relate?
Sure, take the helium neon laser, for example. In that system, the population of electrons in specific energy levels is carefully controlled. When electrons fall from a higher to a lower energy level, they emit light of a very specific wavelength. If you shift or fine tune those energy levels, thanks to understanding electron distributions, you control the exact color of the laser. In other contexts, fine structure details revealed by these shifts help design lasers used in telecommunications or even precision atomic clocks.
How that specific wavelength is controlled, that is very interesting. So, because you are controlling population of electron in specific energy level.
Exactly. In a laser, you use something called population inversion. That's when you get more electrons in an excited state than in a lower one. By precisely managing those energy levels, using atomic structure and external conditions, you produce a predictable narrow wavelength. This coherent light is what we see as a laser beam. It's all about carefully using that knowledge of how electrons occupy those levels.
How electron occupy all those levels. Okay. So, while understanding those transition, we can control, and while controlling, we can design a specific
You've got it. By understanding which transitions happen, meaning which energy levels the electrons move between, we can choose the exact difference in energy. That difference corresponds to a precise wavelength of light. By controlling the environment, the materials, and the energy input, we can design lasers that emit specific colors, whether it's red in a laser pointer or infrared in a telecommunication laser. In short, quantum control equals laser design.
Okay, what one more important example from Zeeman effect?
A classic Zeeman effect example is in astronomy. When we look at light from atoms in a star's atmosphere, we see spectral lines. In the presence of the star's magnetic field, these lines split into multiple components. By measuring that splitting, astronomers can deduce the strength of the magnetic field on the star. This is crucial for understanding phenomena like sunspots or the dynamics of stellar atmospheres. In other words, the Zeeman effect lets us read cosmic magnetic fields. No spaceship needed.
So in the previous case for the Stark effect, I think electric field and the lasers are relevant, and for the magnetic field part, you are discussing about this atmosphere and stars thing. Am I correct on this?
Yes, you've got it. The Stark effect, electric field, often comes into play in controlled lab conditions, like fine-tuning lasers or studying atomic structure. Meanwhile, the Zeeman effect, magnetic field, is key in contexts like astrophysics, where we learn about magnetic fields in stars or even in materials. Both effects, though different fields, are like tools that help us decode the subtle inner workings of atoms across different environments.
Okay, uh, give a conclusion what we have discussed.
So, we've explored how atoms react to external fields. The Stark effect is about shifts in energy levels under an electric field, helping us design lasers and understand atomic structure. The Zeeman effect is about splitting under a magnetic field, helping us measure magnetic fields in stars or materials. Both effects link electron arrangements to energy levels, letting us read the hidden details of atomic structure. In essence, these effects bridge theory and observation, letting us shape and understand both earthly and cosmic phenomena.
So how that reveals the hidden details of atomic structure? Can you explain in detail?
Every atom's electrons occupy certain energy levels. These levels are tied to the internal structure, how many electrons, how they interact, and what orbitals they form. When an electric, Stark, or magnetic Zeeman field is applied, these levels shift or split. By measuring exactly how much they change, we get clues about how electrons were arranged in the first place. For example, if levels shift a certain amount, we can deduce the spacing between energy states, which is related to orbital shape and electron distribution. Essentially, these effects give us a subtle measurement tool to reveal the atom's inner architecture.
Okay, you are suggesting that every atom electron occupies certain energy levels that we know, and these energy levels are tied to the internal structure. Okay, many electrons, how they interact, and what orbitals they form. When Stark or magnetic Zeeman field is applied, these levels shift or split. By measuring how much they change, we clue about how electrons were arranged in the first place. For example, if the level shift at a certain amount, we can reduce the spacing between energy states, which is related to the orbital shape and electron distribution. Can you explain that orbital shapes and electron distribution? So you are talking that if the interaction happen, we label the shift, amount of shift.
Exactly. Each electron sits in an orbital, which is basically a region around the nucleus where it's likely to be found. Different orbitals have different shapes, like spherical for s orbitals or dumbbell shaped for p orbitals. The energy of each orbital depends on how close it is to the nucleus and the interactions with other electrons. When you apply a field, these energy levels change by a specific amount. By measuring the exact shifts, we infer which orbitals were involved. If certain orbitals shift differently, it tells us their original spacing and thus the arrangement of electrons. In short, the shift is like a fingerprint of the atom's internal structure.
Okay, how that mathematically that shift is calculated?
Mathematically, the shift is often calculated using perturbation theory. In simple terms, you treat the external electric or magnetic field as a small disturbance to the atom's existing energy. The first order energy shift is proportional to how strongly the electron's orbital interacts with the field. For the Stark effect, this involves the dipole moment, how far the electron cloud is stretched by the field. For the Zeeman effect, it involves the magnetic moment, how the electron's tiny current loop responds to the field. The shift is then given by well-known formulas, like a constant times the field strength times these moments. In essence, it's a neat, predictable calculation once you know the orbital details.
How electron tiny current loop respond to the field? That is the main idea.
In simple terms, an electron orbiting the nucleus or spinning on its own acts like a tiny loop of current, and such a loop creates a magnetic moment. Basically, it behaves like a little magnet. When you put this mini magnet in an external magnetic field, the energy of the electron changes depending on how it aligns with that field. If the electron's magnetic moment aligns with the external field, the energy is lower. If it's opposite, the energy is higher. This is what causes the Zeeman splitting of energy levels. So the external field tugs on that tiny magnetic property, shifting the energy levels accordingly.
Yeah, that tiny loop of current is very important because it creates a magnetic moment. Basically, it behaves like a little magnet. Okay, and then the energy of the electron change depending how it align with that field. Okay, there is also things are happening like first it behaves like a magnet, and then when magnetic field is applied, doesn't they repel or attract each other? The very first intuition when they heard.
In a way, yes, but it's more subtle. The electron's magnetic moment and the external field don't literally push or pull in a mechanical sense. Instead, the alignment determines the electron's energy state. If the magnetic moment aligns with the field, it's in a lower energy state, and if it's opposite, it's in a higher energy state. In quantum mechanics, this changes the energy levels rather than causing a classical repulsion or attraction. The result is that the energy levels split or shift, which is what we observe in the Zeeman effect.
Okay, thank you.